Hello and welcome again to my Physical Science online lecture video series. In today's video, I wanted to introduce the topic of the chemical elements. Before I begin with that introduction, I wanted to maybe kick off with a little quote from the great physicist Richard Feynman. And Feynman said that if, in some cataclysm, all of scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see there is an enormous amount of information about the world if just a little imagination and thinking are applied. So if this physicist, this well-known physicist, Nobel laureate, Caltech professor, if he were to pass only one piece of scientific knowledge to the next generation of people, and all other knowledge were to be lost in a cataclysm, that one sentence he would pass on is that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. So, in a sense, today's lecture topic is about this. The chemical elements are, in fact, basically the various atomic forms. The various individual atoms are going to be one or another of the chemical elements. So any bit of matter that is broken down to a single atom, that single atom represents one of the 120 or so chemical elements that we now know to exist one way or another. I should add that there may be 120 or so elements so far discovered, maybe a few more. Only 88 have been encountered so far in actual nature. All the others are artificially created using, for example, like a particle smashers, that kind of thing. The way that chemists classify matter is as follows. First of all, matter itself is basically anything which has mass. So, my body's made of matter, the wall's made of matter, the camera's made of matter, etc. Protons and electrons and neutrons and muons and so on are matter. Photons, of course, are massless, although they carry momentum, so you could argue that they're not matter per se. But most of what we interact with is matter. And so chemists can break up matter into several classes. The first class is pure substances, which in turn can be anything that is simply an element, or anything which is a molecular compound of two or more elements. Could arguably be a pure substance. Certainly you can have molecular compounds. You can have a molecule that contains two or more different elements, and you can also have a molecule that contains two or more of only the same element. So for example, oxygen usually exists as the molecule O2. There's two oxygen atoms, or oxygen being the element, oxygen being an atom, and two of them combined being a molecule. And then after that, there are various types of mixtures. So we can dissolve salt in water, for example, or we can mix several types of, like silicates together, like sand, for example, sand plus dirt or whatever. So the trick with the elements themselves is that they are usually sort of organized into what's called the periodic table of the element. And that is broken into different periods and different groups. There's actually 17 periods and 18 different groups of elements. The periods are basically the individual rows, and the groups are the columns in the table. So, for example, if you were to pull up a periodic table, you'd notice that hydrogen and lithium are both in the same column. That means they're both in group 1A. For example, helium and argon and krypton are all noble gases. They're all in group, you call it group 8 or group 18, noble gas group. Helium and hydrogen are both in the first row, so they're in the same period together, and so on. So what is it that actually separates one element from another? What is it that changes something from being, say, a helium atom into being a carbon atom? Or what's the difference between a nitrogen atom and an oxygen atom and a fluorine atom? What is it that differentiates the different elements? Well, basically what an atom consists of is a nucleus, which is made up of protons and sometimes also, or maybe I should say usually also, neutrons. And then it also has a shell of electrons orbiting it. So the shell of electrons in basic neutral state is going to have the same number of electrons as there are protons in the core. But you can ionize atoms, and many atoms are very easily ionizable, so that they have either more electrons or fewer electrons than the number of protons in the core. And all that means is that it's going to have some charge to it. The atom as a whole now has a charge to it. But that itself doesn't actually change what element that atom is, or whether the atom's an oxygen or a carbon or a nitrogen or what have you, a hydrogen or a helium. So it's not the electron, the number of electrons or the configuration of the electrons that necessarily affects whether what kind of element we're dealing with. So instead we have to look in the core of the atom. And as I said, there's basically two general types of particle that sit in the core. There's protons and there's neutrons. And so with those two types of things, there's actually three things that can be varied, right? There's how many protons are in the core, there's how many neutrons are in the core, and there's how many total nucleons, where a nucleon is a proton or a neutron, is in the core. So 3 things that can be varied. And it turns out that the only one of those 3 that matters as to what atom it is the number of protons. So hydrogen has 1 proton, and any atom that has 1 proton is a hydrogen. Helium has 2 protons. Any atom that has 2 protons and not 3 or 1 or what have you is a helium atom, and so on. So it turns out that you can change the number of neutrons and therefore the total number of nucleons in an atom, and it's still the same atom. And what we call that is isotopes. So for hydrogen, for example, there's 3, I will call them common isotopes in as much as that they do occur in nature, that we've encountered. There's hydrogen, the most common one just has a single proton in the nucleus and no other particles. The next most common is sometimes called deuterium, and that one has 2 particles in the nucleus, 1 proton and 1 neutron. And the tritium is relatively rare, but does occur. It's actually used in fusion research sometimes. And that one contains a single proton and 2 neutrons. And so on. So helium could have 2 protons and a neutron. It can have 2 protons and 3 neutrons. Usually it has 2 protons and 2 neutrons. And it turns out that the number of neutrons has some effect on how stable the atom is. You know, if you took an atom that had, oxygen and you remove all the neutrons, it would be a very unstable atom. It would tend to fission apart into other atoms. The nucleus would tend to want to explode away because all these positively charged protons are in close proximity to each other. And basically what happens is that there's a fundamental force in nature called the nuclear strong force, which is a very short-range force that helps hold these nuclei together, because otherwise the nuclei is entirely positively charged and would tend to want to explode away. So much of the properties of an individual atom, an individual element, depend on some combination between the fact that it has a set number of protons in the nucleus and that the orbits of the electrons around the nucleus are fixed into given configurations. And so it turns out that there's different orbital shells, and there's a certain number of electrons that any given shell wants to have to be in its most stable state. For example, hydrogen and helium both tend to want to have 2 electrons in their orbit, although hydrogen often will give away its 1 electron and go to 0, which is also reasonably stable. Fluorine and oxygen and nitrogen want to have 8 in their shell. And so this helps determine how easily they will be ionized by either accepting or giving away an electron, and how easily they'll combine with other elements. So I think that's about all the time I have for today's introductory video. I hope you enjoyed this video, and thank you for watching.